Okay, welcome to the notes file for lesson 10.8, probability of compound events. In this lesson, we're going to be finding the number of outcomes for an event, and the events we're going to be doing are going to be compound events. So that's a vocabulary term. It's a pretty simple idea, but it may be a little bit new to you. We're also going to be finding the probability of a compound event. We're going to use various methods on here. One method is a tree diagram. I'm honestly not a huge fan of tree diagrams because I have trouble keeping them nice and neat, but it is a decent little visual as long as there aren't too many possibilities. So we're going to be finding outcomes of compound events. So let's make sure we're clear what a compound event is. A compound event consists of two or more simple events. A simple event is like flipping a coin, flicking a spinner, rolling a number cube, drawing a card from a deck. A simple event. If you do two or more of those, the entire thing is called a compound event. Similar to a compound word, it consists of two regular words put together. Well, that's all a compound event is. They can be pretty simplistic, like flipping a coin and then flipping another coin, so flipping two coins. Or it could be kind of involved. It could be flipping a coin, flicking a spinner, drawing a card, rolling a number cube. It could be a combination of a bunch of things. The probability of a compound event is the fraction of outcomes in the sample space for which the compound event occurs. So if I am trying to find the probability of a coin landing on heads or landing on tails, I'm also going to be going into the probability of, if I flip two coins, what's the probability of them both being heads, or of one being heads and one being tails? We'll be able to do those if we can figure out the number of outcomes. So that's the first little part. We're going to be finding the outcomes. When we're working with compound events, you can make a table. I like making a table. You can draw a tree diagram. I'll tell you right now, I don't love tree diagrams. We can make a list, which is just basically the same thing as a table, only tables kind of a rectangular arrangement of the things that would be in the list. And we're even going to, when we get to the end, we're going to go over a method of not having to make those lists, where we can figure out how many outcomes there are without doing the list, which is super handy. So let's take a look at some examples here. Let me turn this stuff off so we can see what's going on. In example one, a pet store sells aquariums in three shapes, hexagon, pentagons, and rectangles, and two sizes, 10 gallons and 20 gallons. How many different fish tanks can be made from the different shapes and sizes? So it says here you can use a table, and that's what's here, or a tree diagram. So they do it two different ways. When you're doing yours, you do not need to do it two different ways. Do it whichever way you prefer. So let's take a look at that. They made a table, shapes and sizes. So they chose hexagon for the shape, and that could be 10 gallons. But they could also choose pentagon for the shape, with it being 10 gallons, or a rectangle for the shape, 10 gallons. And then they went through those same three shapes again with the 20-gallon size. So how many rows you end up with here, there ends up being 6 rows. That's how many combinations or how many different fish tanks can be made with those three shapes and those two sizes. So here's a tree diagram. It has the exact same information, just kind of reordered a little bit. Here they have hexagon, and they have two branches because there's two different sizes that I could get if I picked the hexagon shape. There's two branches coming off pentagon because there's two different sizes. There's two branches coming off the rectangle because there's two different sizes. And then the number of outcomes we end up with here is again 6. There's hexagon 10 gallon, hexagon 20 gallon. And we can actually see those things right here. Here's hexagon 10 gallon and hexagon 20 gallon. That's these two right here. And then we have pentagon 10 gallon and pentagon 20 gallon. That's here and here. And then this last block rectangle 10 gallon, rectangle 20 gallon, that's right here. So that one and that one. It's the exact same information. I prefer doing it like this, but if you list them out like this, you have to be careful that you do it in an orderly way. There aren't that many combinations here, so this one is fairly straightforward, but it can get a little bit messy. These, for me personally, get really messy if there's a lot of possible outcomes. So I generally kind of stay away from tree diagrams just because I struggle with my neatness. If you can do these neatly, these are pretty nice. 1, 2, 3, 4, 5, 6 combos. There it is. There's 6 branches. 1, 2, 3, 4, 5, 6. It ends up being 6 ends over here. This works kind of nicely if you have multiple things instead of just shape and size. But like if there was a color in there as well, then we just have more branches coming off here. Again, tree diagrams work. They just can be a little messy for me. So let's take a look at got it number 1. So got it number 1, it says Miranda has 5 shirts and 4 pairs of pants that she wants to use for her work clothes. How many different outfits can be assembled using 5 shirts and 4 pairs of pants? So there's different ways I can do it. Here's the way I'm going to choose to do it. I'm going to use a table. So if I have a table, I need to have, okay, shirts and then pants. And so I'm going to arrange my results in a table format. And then my shirts, I have 5 shirts. If I know the shirts are going to go in this underneath the shirts one, what I can do is I can just number 1, 2, 3, 4, and 5. And then for the pants, I can number those as well. 1, 2, 3, and 4, because there's 4 pairs of pants with 5 shirts. I won't get confused on what the number means because it's going to be in the shirts column. So I can choose shirt 1, pant 1. I can choose shirt 1 and choose pant 2. Shirt 1 and pant 3. Shirt 1 and pant 4. And that's all the pairs of pants I have. So those are the combinations for choosing shirt 1. But there's nothing that says I have to choose shirt 1. I could choose shirt 2. If I choose shirt 2, I can use pants 1, pants 2, pants 3, and pants 4. Or I could choose shirt number 3. Shirt 3, I can wear pants 1, pants 2, pants 3, and pants 4. And I'm going to continue this list up here. So shirts and pants. So if we look at it, there are 4 combos because there's 4 pair of pants with shirt 1. There's 4 pair of pants with shirt 2, 4 pair of pants with shirt 3. Or I could do shirt 4 and do pants 1, shirt 4 with pants 2, shirt 4 with pants 3, and shirts 4 with pants 4. And lastly, I could choose the 5th shirt and do pants 1. Or I can do the 5th shirt with pants 2, the 5th shirt with pants 3, and the 5th shirt with pants 4. And so there are all my possible combinations. There's 4, 4, 4, 4, and 4. That is 20 outfits that she could make. So if you think about it, working 5 days a week, that means you can go 4 weeks without repeating an outfit. It might look very similar with only 5 shirts in the mix, but it would technically be, there's 20 different outfits. Now, if you use a tree diagram, here's kind of why I don't love tree diagrams. If you did a tree diagram, you have Miranda here. She can, first selection she's going to pick is a shirt. So here's what it looked like. She could do shirt 1, shirt 2, shirt 3, shirt 4, or shirt 5. And the reason I had to spread these out because after she picks a shirt, she has to pick a pair of pants. And there are 4 pairs of pants. So she could do 1, 2, 3, 4. And that's all with shirt 1. And then do 1, 2, 3, 4. And that's all for shirt 2. And you see my branches are starting to kind of pile up here. 1, 2, 3, and 4. 1, 2, 3, and 4. 1, 2, 3, and 4. 1, 2, 3, 4. And then I'll cram the last one here. 1, 2, 3, and 4. 1, 2, 3, 4. And so if you count up all these from here all the way down to there, 4, 4, 4, 4, 4. There's 5 sets of 4. There's 20. Just like we got here, this can get a little bit messy. Now, if you had also, oh, I don't know, a belt in the mix, 2 belts, and there's going to be 2 branches coming off each of these, this can get really messy. This can get kind of lengthy, but I can do these a little bit more neatly since it's nice rows and columns. Nothing wrong with either one, whichever you prefer. I personally like arranging stuff in a table form or listing it out, but I can do that in an orderly fashion. When you're listing them out, you have to make sure you do it in a very orderly fashion. If you're doing a tree diagram, make sure you do that very neatly. So let's take a look at the next little example here. The example 2. Example 2 gets into making an orderly list. They arranged it in rows and columns so you can kind of see things easier. But it says in example 2, students are assigned a temporary password the first time they visit a computer lab. Temporary passwords consist of a letter, and that letter is going to be an A, a B, or a C. Only 3 letter choices there. Followed by a number, and the number is either going to be a 1 or a 2. Followed by a letter, and that letter is going to be either an X, a Y, or a Z. So very limited choices. It's either an A, B, or a C, a 1 or a 2, and then an X, Y, or Z. And it wants to know how many different temporary passwords are there. If we're going to make a list, we need to do it in a very orderly way. So look at what they did here. The first letter here is an A because that is the first letter choice. And the first number is the 1 because that is the first number choice. And the first letter here is the X because that is the first letter choice there. So A1X, they picked the first option of each one. But then here's what's critical. They kept the A and the 1 and just changed the X to the next letter in this set. So they changed it to a Y to get another combination. And then they changed the Y to a Z and to get this one. So it's critical that we see how this first little block here, A1, and then they cycled through the X, the Y, and the Z. There's 3 combos there. But then look at what they did from here to here. They simply kept the A and changed the 1 to a 2, and then again cycled through the X, Y, and Z. So this group of 3 follows this group of 3, and these are all the possible combinations or passwords using the A. So there's 3 because we cycled through X, Y, and Z, and then these 3 is because they cycled through X, Y, and Z again, only choosing a 2 for the number. And so there are 6 passwords possible using the A. But then look at from here to here. All they did was change the A to a B. Everything else is exactly the same. They did a number 1, number 1, number 1 with the X, Y, and the Z. And then the number 2, the number 2, the number 2 with the X, the Y, and the Z. So there's 6 more using the B. And then, look here. They changed the B to a C, and again, that 1X, 1Y, 1Z, 2X, 2Y, 2Z, there's 6 more there. So there's 6 columns with 3 in each column. 6 times 3 is 18. There are 18 total different passwords that you can come up with there. Now, obviously, I hope if you added in a letter possibility, that would add in another row of possibilities, increasing the number of outcomes. If you add in number choices, that's going to add on columns. So if you added a 3 in the possibility, you're going to have another set of columns here where you put a 3 as the number. So that's why they want you to have like long passwords and stuff if you are picking them yourself. So there are 3 different temporary or passwords using an A and a 1, and then 3 different temporary passwords using an A and a 2, and then a B1, B2, end up being 18 altogether. You could have done a little branched out tree diagram. If you wanted to do a tree diagram, you could have. Here's kind of what that would look like. I would go with, okay, I could pick an A, I could pick a B, or I could pick a C. If I pick an A, I can go with a 1 or a 2. If I pick the B, I could pick a 1 or a 2. If I pick the C, I could pick a 1 or a 2. If I picked an A and a 1, then I could pick either an X, a Y, or a Z. If I picked a 2, I could pick the X, the Y, or the Z. And so on. But look, my branches are going to start getting piled up here. I can't write small enough. I can't do this neatly, but I could do an X, a Y, and a Z. And then from the 2, I could have an X, a Y, and a Z. And I could keep going. There's 3 branches coming off this 1, 1, 2, 3. There's 3 branches coming off the 2, 1, 2, 3. We're going to have an X, a Y, and a Z, an X, a Y, and a Z. You're going to have 6 sets of 3, just like we had before. There's the 6 sets of 3. I don't love the tree diagrams because I have trouble keeping them nice and neat. I prefer listing stuff here and listing it in a very orderly fashion. So there's 18 different passwords. So let's take a look at example, or got it number 2. Got it number 2 is about a pizza. So a pizza shop has regular, deep dish, and thin crust, 2 different cheeses, and 5 toppings. How many different 1 cheese and 1 topping pizzas can be ordered? So I'm going to use a table. I prefer a table, so here's what I'm going to do. I'm going to have the crust choice, and then I'm going to have the cheese choice, and then I'm going to have the topping. And I'm not going to use any names or anything at all. I'm going to call it regular, deep dish, and thin crust. Let's have an R, a D, and T. And then to keep things nice and simple, we have 2 different cheeses. Let's call it cheese 1 and cheese 2. And we have 5 toppings. Well, I might think, oh, I don't want to use a 1 or 2, but they're going to be in a different column here. So I'm just going to use 1, 2, 3, 4, and 5 for my toppings. And since they're in different columns, I'll be able to keep it separate. So I'm going to pick regular crust, cheese 1, topping 1. That's my first combination. Regular crust, cheese 1, topping 1. And now I'm going to do it in a very orderly fashion. I'm going to keep the crust, keep the cheese, but change the topping. So regular, cheese 1, topping 2. Regular, cheese 1, topping 3. Regular, cheese 1, topping 4. Regular, cheese 1, topping 5. And now I have done all the possible regular cheese 1s, but now I'm going to change cheese 1 to cheese 2. So what if I did regular cheese 2? Well, then I could do topping 1, or I could do cheese 2 with topping 2. I could do cheese 2 with topping 3. I could do regular cheese 2 topping 4, or regular cheese 2 topping 5. And I end up with 10 possible pizzas. It's 2 blocks of 5 here. 10 possible pizzas using a regular crust. So if I keep my format the same, you should be able to create the next little block of possibilities very easily. Just change the crust, change it to a deep dish crust, and go through the exact same combinations. I hope it's not a surprise that there's going to be 10 of them with the deep dish, because I could do 1, 1, 1 with 2, 1 with 3, 1 with 4, and 1 with 5, exactly like I had with the regular crust. And then we're going to have deep dish cheese 2 with topping 1, cheese 2 with topping 2, cheese 2 with topping 3, cheese 2 with topping 4, and cheese 2 with topping 5. So there's 10 more. Well, how many do you think there's going to be if I use a thin crust? Well, exactly 10 more. It's going to be crust, cheese, topping. And so I could have thin crust with cheese 1 and topping 1, thin 1, 2, thin 1, 3, thin 1, 4, and thin 1, 5. Or I could do thin 1 with cheese 2 and go through those 5 toppings. Cheese 2 with topping 2, topping 3, topping 4, and topping 5. And so we end up with 10 more. And so there's a total of 30 different pizza combinations you could come up with there. Now, that's definitely not the only way to come up with that answer. There are shortcut ways. You should see that there are 5, and then there's 6 blocks of 5. Why is there 6? Well, because there's 3 columns and 2 blocks of each. There's 2 cheeses and 3 crust. There is a shortcut way we can be doing these things that will assist us. Listing things out, that's an important sort of skill, but you need to be doing it in a very orderly fashion. So let's move on. And the next thing we're going to be doing is finding the probability of a compound event. And wonderfully enough, there's different ways of doing this that can make it super duper easy. So let's take a look at example 3 here. Example 3, Emilio has 2 counters. Each counter has one side marked with an E and the other side marked with a J. So the E is for Emilio, the J is for Jacob. Both counters are tossed, so they're like coins basically. Both counters are tossed. If one counter lands with an E up and the other lands with a J up, then Emilio wins. So if there's an E on one and a J on the other, then Emilio wins. Otherwise, Jacob wins. So what's the probability that Emilio will win? So the first thing we have to do, first we got to find the outcomes. So here they just listed them out. So you have a counter, they could both land on E. So you could have an E and an E. That's one possibility. You could have an E on this one and a J on that one. That's another possibility. You could have a J on this one and an E on that one. That's another possibility. Or they could both be J's. And that's a fourth possibility. So there's only 4 possible outcomes. There's only 4. So the probability that Emilio was going to win, so an Emilio win, the probability is going to be out of 4 because there's 4 possible outcomes. Well, how many of these 4 is it where one counter lands with an E and one lands with a J? Well, these 2 right here. 2 of these 4 combinations have an E and a J. And that's what it says it needs to be for Emilio to win. If one counter lands with E up and the other lands with J up, Emilio wins. So Emilio's going to win on these. He will lose if they're both Emilio or both E's or both J's. So this ends up being a half or 50%. So it's a fair game. Emilio's should win about half the time, and Jacob should win the other half. So let's take a look at example 3, or got it number 3. I will tell you, I looked at this problem earlier, and I don't like the question. And I'll talk about why. I think it is a very confusing question, and it's going to lead into the little counting principle that we're going to be talking about next. But here's why I don't like this question. I'm not sure exactly what it's asking, and I'll try to get you to see why I think it's confusing. It says, what is the probability of randomly choosing a 5-letter password that consists of only vowels if each vowel can be used more than once? So here's where I get confused. I don't know if it's wanting me to pick a 5-letter password that consists of only vowels, and can I guess the password? Or is it the probability of picking a password that consists of only vowels? And then am I only picking letters? Can I use numbers? See, I think it's a little confusing. So I'm going to interpret this as the probability if there is a password. So I'm going to have that. I'm going to know that the password only has vowels, and I'm going to try to figure out the probability that I can pick it. I can guess the password. I don't know if that's what they mean by this question here or not, but that's what I'm going to go with. I'm going to go with there's some password that is 5 vowels. And you can use the vowels more than once. So the vowels are A, E, I, O, and U. So a possible password would be all A's. That is a possible password. Or it could be an A, an A, an A, an A, and an E. Or it could be an A, an A, an A, an A, and an I, and so on. And then we could cycle. Man, making that list is going to be an absolute nightmare, right? It's going to be terrible because we're going to have a 5-letter password, and then there's 5 choices for each letter, and it can be a nightmare listing them out. So here's what I am going to do. I am going to use what's called a fundamental counting principle. So let's take a look at, I don't really want to do this listing out business. So I want to do a fundamental counting principle here and think about it. How many different letters could go here? Well, if they're all vowels, there's 5 choices, right? I have 5 choices for the first letter. And if I can repeat, there's also 5 choices for the second letter. And if I could repeat, there's also 5 choices for the third letter. And 5 choices for the fourth letter. And 5 choices for the fifth letter. There's 5 choices on each of the 5 letters of the password. So if there's 5 choices here, and 5 choices here, and 5 here, 5 here, 5 here, that's a lot of possibilities if I cycle them through, and I don't want to list all this out. So here's a little, and I'll summarize it here a little bit on the next picture, but here's what I can do. There's a fundamental counting principle that says that there's 5 ways I could do this, and 5 ways to do that, and 5 to do that, and 5 that. The fundamental counting principle says, hey, to figure out the total number of ways, you can just multiply these things together. So if you take 5 times 5 times 5 times 5 times 5, I get 3,125. So there's 3,125 possible outcomes or possible passwords here. So just using only vowels and knowing that it's 5 letters, that's still 3,125 possible passwords. Now you see why I didn't want to list it out. So I don't know that that is what they were intending with this question. That's how I interpreted it. So the probability of me choosing the right password, the probability of getting the password correct, if I randomly guess it, well, there's only one right password out of the 3,125 possible ones. Not very likely. However, if you think about it, if you use a password, you're not going to use just vowels. So you're going to have more than 5 possibilities. And then you might also have tried to create a password and they say, hey, you have to use a number. Well, there's 26 letters of the alphabet. If I could use any letter of the alphabet, but only letters, each of these 5s are going to turn into a 26, and that's going to crank this number way high. And then if you think about it, whoa, there's 10 digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. That would make 36 possible ones. And then you say, oh, you have to use a capital letter. If capital letters are different than lowercase, that adds on 26 more possibilities. So now we're up to 62 on each one. And then if you can use symbols plus symbols in there, you can have a bunch more. All that does is it adds in possibilities here. So if you change each of these to a much bigger number, and then you multiply them all together, you get a huge number of possible passwords, and that makes it more secure. So this fundamental counting principle saves me a ton of time from having to list those things out. So let's kind of summarize the fundamental counting principle here. The fundamental counting principle, here it is in kind of generic, but let's just look at the example. If there's 4 possible sizes for fish tanks and 3 possible shapes, then there are 4 times 3. Just take 4 times 3, and there's 12. So let's do a quick couple of examples here. If you flip 5 coins, how many possible outcomes? So if I want to know the number of possible outcomes, I could list those all out, but how about this? There's 2 things that could happen on the first coin, 2 things that could happen on the second coin, 2 things that could happen on the third coin, 2 things that could happen on the fourth coin, and 2 things that could happen on the 5th coin. The fundamental counting principle says I can just multiply all those together, and you get 32. So there's 32 possible outcomes when you flip 5 coins, because there's 2 on each. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. There's 32 possible outcomes. So how about this? What if I flip a coin? So I'll flip a coin, roll a number cube, and then draw a card from a deck. How many things could happen when you flip a coin? 2. How many things could happen when you roll a number cube? 6. How many things could happen when you draw a card? Well, assuming no jokers, there's 52 cards in a deck. This would be an absolute nightmare to list out all the possibilities, but the fundamental counting principle says that I can just multiply 2 times 6 times 52, and that is 624 possible outcomes. It makes it so easy to figure out the total number of outcomes. Make sure you take advantage of this. It's super duper wonderful. So let's take a look at this next example here. So this has worked out for us. Example 4, Lamar is going to spin each spinner once. What is the probability that he will spin red and the 9? The number 9. So probability that he gets it to be red on this spinner and 9 here. Well, if we want to know the total possibilities, we just need to know how many things could happen on this spinner. So if you look at it, how many things? Well, 1, 2, 3, 4, 5. There's 5 sectors, so there's 5 things that could happen. Here, there's 10 sectors, so there's 10 things that could happen. And then the fundamental counting principle says that I can just multiply 5 times 10. There are 50 possible outcomes. But only one of those 50 is getting a red with a 9. And so it's 1 out of 50, or 2%. But here's actually an awesome way of doing this problem. If he wants to get a red and the number 9, what's the probability that this one's going to land on red? Well, it's 1 out of 1, 2, 3, 4, 5 sectors. What's the probability this one's going to land on the number 9? Well, there's 1 9 out of 10 sectors. The fundamental counting principle even works for probabilities. You can just find this probability and this probability. When you multiply them together, you get the exact same result. So if you can do simple probability and multiply fractions together with a calculator, you can do these as well. You can do it by finding the outcomes, or you can do it as individual probabilities and multiply them together. I like this way right here. This way, to me, makes sense. This is the probability of getting a red on the first one. And this is the probability of getting 9 on the second one, and then I can just multiply those two probabilities together. Super duper simple. So let's take a look at this next little example here. Example 4, 3 number cubes are rolled. What is the probability of rolling 3 5s? So when you roll a number cube, there's 6 things that could happen. If you roll 3 of them, there's 6 things that could happen, 6 things that could happen, 6 things that could happen. So the fundamental counting principle says I can multiply those together to get the number of possible outcomes. So 6 times 6 times 6 is 216. There's 216 things that could happen, but only one of them is getting all 3 5s. So the probability of getting all 5s is 1 out of 216. So the fundamental counting principle says I can take 6 times 6 times 6 because that's how many things that could happen on each one. However, what I can do is say, hey, what's the probability of getting a 6 on the first one? Oh, not a 6. Probability of getting a 5. We're trying to get a 5. The probability of getting a 5 on the first one is 1 out of 6. On the second one, the probability of getting a 5 on that one is also 1 out of 6. And on the third one, the probability of getting a 5 is 1 out of 6. And then if I multiply these 3 fractions together, I get that exact same result. 1 times 1 times 1 is the 1. 6 times 6 times 6 is the 216. So the probability of you rolling 3 5s is incredibly unlikely, 1 time out of every 216 times on average. So the fundamental counting principle, super wonderful. Make sure you take advantage of that. It makes problems like, hey, I have 3 ties and 4 shirts and 5 pair of pants and let's say 10 pair of socks. How many different outfits can I do? Just multiply them all together. Super crazy fast. 3 times 4 is 12, times 5 is 60, times 10. There's 600 outfits you can do there. All you do is multiply, and think about it. If you tried to list them all out, that would be an absolute nightmare because there's so many of them. The fundamental counting principle also makes stuff like this really easy. Hey, I am going to create a password. And let's say the password is all letters. And let's say it is, let's say it's only a 4-letter password. Doesn't sound very secure, but how many choices if I have to pick letters? Well, there's 26 choices for the first letter, 26 for the second letter, 26 for the third letter, 26 for the fourth. The fundamental counting principle says that I can just multiply all those together. 26 times itself 4 times, you're going to get 456,976 different possibilities. If these had to be numbers instead, the problem would simply change to all 10s. And you're going to end up with only 10,000 different passwords if they had to be numbers. So this would be all numbers. This would be all letters. Now, if it could be either or, then they're going to all change to 36s. If they could be capital letters, it's going to increase all those again, and it makes it just bigger and bigger number of possibilities.